Hi, hi everyone. So this is just a video to initiate your assignment for ENG777, Mechanical Engineering Systems Modeling and Simulation. So if you look at the assignment, there are two steps. So we've got your step one, which is conduct a numerical validation case using the smooth tube against the theoretical values for Nusselt number and Darcy friction factor. So we've got the Nusselt number equation here. And we have the Darcy friction factor, equation 1 and equation 2. So equation 2 is straightforward. We can calculate the Darcy friction factor for the smooth tube by varying the Reynolds number. And equation 1 is something where we can extract the Darcy friction factor from ANSYS by measuring the delta pressure from the inlet of the tube. And this will give us delta pressure, and by here we can compare equation 1 with equation 2 to compare our results. So we can also backward calculate, rearrange this equation to see what delta pressure should be in order to see if we're moving in the right direction or wrong direction. So the first thing that you have to do is obviously using the kind of parameters provided in here in order to create an Excel sheet. Because the first thing it says is select a range of Reynolds numbers, okay, between 4,000 and 10,000 to calculate theoretical values of Nusselt number and friction factor for a smooth tube. Then what we're going to be doing is generating a 3D numerical model of the smooth tube using ANSYS and ensuring that the mesh, boundary condition and solver are adequate for determined turbulence modeling. Once we've done that, then we're going to conduct a turbulence dependency study to ensure that the correct turbulence model and appropriate wall functions are utilized for all future simulations. Then we determine the Nusselt number and friction factor from ANSYS simulation and compare with theoretical values and discuss the findings to ensure all appropriate measures are considered before moving forward. So let's look at step 1 first. So step 1 requires us to produce this table. So you can see here, so I've done the Reynolds number going from 4,000, 5,000, 6,000, 7,000 all the way to 10,000. So giving me a total of 1, 2, 3, 4, 5, 6, 7 measurement points for my graph. I then calculated the Reynolds number for these, the velocity for each flow. Then using the equation 2, I can calculate the Darcy friction factor. And then obviously using the Nusselt number, I calculate the theoretical Nusselt number. From these, again, using the equation, I can calculate the heat transfer coefficient that needs to be applied into ANSYS. This can be found in the equation. And then, as I said, rearranging the equation, you can actually find the theoretical delta pressure, which will help you going forward. So you can see here on the graph here, I've done already a validation case where the numerical calculated versus the numerical are in very good agreement. So let's see how this is done now. So I'll let you guys deal with the maths side of things in order to get the Excel sheet up and ready. So the first thing we're going to do is open up ANSYS and go straight to Workbench. Give it a few seconds to load up. Okay, so once it's opened up, File, Save As, create a good working directory. As I said, if you're using ANSYS in the university computers, you can create it on the desktop as a working folder. And then once you finish, you can copy that folder onto a USB key. You can also run it from a USB key. It's much faster running it from the desktop and then copying it. ANSYS doesn't not like working from your OneDrive, so try and avoid that. But once you've done everything, you can always upload it to OneDrive afterwards and then re-download it again to carry on with your work. Please do not leave anything on the desktop on the university computers, as they are wiped every so often, so you will lose your work. So and again, I'm just giving you fair warning, do not leave anything on the desktop on individual computers, as they will be removed. So once you've created your working directory, you're going to go straight to Fluid Flow Fluent and name this one Smooth Tube, and then right click and then open up Design Modeler. So I've provided all the dimensions So we know the length of the tube is 400 mil and the diameter is 20. So we don't need to sketch anything. We can just go straight to primitive shape. Go to cylinder, change that one to YZ. So it's in this direction. As I said, it's 10 radius and 400. But what we're going to do is we're going to do 400. But then we're going to go minus 200 to keep it nice and center in the middle, because when we do the spiral groove, we'll do it in the center and it's just easier doing it this way. So press generate. So we have our tube here. So we'll go file, on here, make sure it's a fluid, and call it smooth tube or just tube for general, and then press generate for good luck, file, close, design modeler. We'll then go on to the mesh. Okay, so once the mesh is in here, I've always do mine in wireframe. It just makes it easier for me to see what's happening. But you can change that to, to have it as a shaded or solid. It's up to you. But I think as wireframe, it just makes it nice and easier. So having it like this, select the face, and then obviously here, inlet, by pressing N on the keyboard, it just pops up this name selection, inlet. Select the back end, N on the keyboard, outlet, and then selecting the surface here, wall. Okay, so mesh wise here, okay, we're going to generate insert method. We're going to put triangular mesh, tetrahedrons, and what we're going to do is we're going to insert inflation, because we're working with heat transfer. So select the body, and the name selection is going to be wall. Press enter on the keyboard, or I think you can double click. Nope, enter on the keyboard, you'll select the wall, and we're going to put 10 layers. Okay, and the mesh side here, click on sizing, and then here we want to capture curvature, no. And then here the sizing here, you can see 40 millimeters is the outer circle, 20 is the inner circle. What we're going to do is just put that to 2.5 there. That should be fine. Generate mesh. Now you can do a mesh dependency study, but depending on the amount of effort that's needed on this, I would be very skeptical, because if you're using a student version license, you will be limited to the number of elements. If you're here on campus, I guess you can do a mesh dependency, but it's not a requirement, and I would refrain from not going down that path. But this mesh here is quite adequate to do this analysis. Student and full version. So we have everything that we needed here, so let's go to the tube, and as the tube is going to be filled in with water, so create name selection and just put this as water. So we know it's going to be water fluid in here. Okay, so we have that there, and we have all of our name selections, we have everything. Leaving the mesh open, selecting the mesh, and then pressing update mesh here is a lot quicker, and you can see here it's generated the mesh. Otherwise, you can close it down, and as I said, so by closing this one down now, you can, on the tree here, right click and update mesh there. But either way, it's fine. So double click on setup. Now I'm going to use 8 cores because the university has 8 processors. We can use that. If you're using it on a student version, you're limited to 4 number of cores. So again, dependent on how you're going to run this, it's up to you. So press start. So once it's loaded up, you can see it's displaying here the inlet and then the outlet. Now obviously we want to turn gravity on, minus 9.81. And what we want to do is we want to go straight to material, and in the material we want to select from Fluent database water liquid. So copy that. And then on the solids we want to bring in structural steel. So copy, close, change, create, close. Now again in the fluid, water liquid, you can see here we can change that to 1000. To keep it consistent with what's been provided, and 0.001 there, change, and then see that's absolutely fine. So making sure that everything's there, we've got water, air, steel, aluminium. We just want to make sure that our reference cell zone are correct. So clicking on the water liquid, we can see that the material name is air. We want to change that to water liquid, apply, close. And now in the models, we want to turn on the energy equation because we're doing a heat transfer problem. So turn on the energy equation, press OK. So that's fine. Now here is where you want to do the parametric study. So you have your spot almas, you've got your K epsilon, and you've got your K omega. Now with the spot almas, I wouldn't bother, but the K epsilon is the ideal one that you want to choose rather than the K omega SST model. So selecting the K epsilon model is where we're going to start with, and then you've got a variety of different wall functions here. Now you've got the standard wall function, scalable wall function, non-equilibrium wall function, enhanced wall treatment, but you also got the RNG and the realizable functions as well. So this is where you will do your parametric study in order to see which turbulence model is the best. So again, you can do one with the K omega as well, but the K epsilon is the ideal one to work through the standard wall function. So what we'll do is we'll keep the K epsilon, we'll keep the standard wall function starting off as our base model, and then obviously you can run it through different variations. So by pressing OK on this, we're going to start with that. We then go to the boundary condition, and in the inlet, before we go in there, we want to change the units. Press T on the keyboard, brings up temperature, we'll change that to degrees Celsius. Now in the edit, we're going to enter and we're going to select one of our velocities. So in here we can see we've got our velocities here. So for example, let's just pick 0.2 meters per second. So 0.2 meters per second, press apply. We're going to put the thermal in as 100 degrees Celsius, as it's coming in at 100 degrees Celsius. Press apply, close. Now the outlet is going to be a pressure outlet, so it's going to be set as 0. And the wall, we click on this, and what we want to do is we want to say that it's a thermal wall. It's made out of steel, but it has a convection, and that convection is calculated from the equation here. So we've got a heat transfer coefficient, 1142.33. So 1142.33. Okay. There's no point putting a wall thickness or anything. It won't make a huge difference. But that's it's that. So freezing temperature, leave that as normal. So 26.85 standard. Press apply, close. So now what we're going to do is we're going to go to initialization, and here we'll leave it as the hybrid. Hybrid initialization usually very good for multiple inlets, but here it should be fine. So press initialize, and as you can see, it comes up with this, which is absolutely fine, not a problem. It just means that the mesh could be utilized a bit more better, but it's fine. So we're going to run the calculation for 1,000, and let that run. And what you'll find, it doesn't take that long, and it'll be completed. So you can see around about 41 iterations it was converged, and the solution was done. So now obviously what we can do is we can have a look at what's happening in here. So we could go create plane, and in the XY plane, call it MCP, mid-cut plane, put 0 in here, create, close, we can go to the graphics, contours, and in here you can look at the static pressure of that mid-cut plane if you wished. So you can see the static pressure, what's happening here. You can also look at the temperature, the total temperature as well. So you can see here, and you can see that it's cooling down a lot quicker. But again, is that correct or not? That's something that we need to investigate. You can also at the same time create a line rake. So the line rake here, we can say, well, we know 0, 0 is absolutely in the middle. So we can say minus 0.2, which is minus 200, plus 0.2, and call that one midline. Create, close, close. And what you can do with that now is you can create an XY plot, and X equals 1, temperature, total temperature, mid-cut line, plot, and you can see that the temperature going from 100 degrees is cooled down to around about 96 degrees Celsius. And you can also do a velocity as well, to see what's happening with the velocity. You know, as the velocity increases, it stabilizes around about that kind of 2.6 meters per second. You know, even though it was coming in a lot much, sorry, 0.02 meters per second. Now, the key thing here is obviously we want to look at the Darcy friction factor and the temperature gradient. So what we want to do here is look at the reference values. So report surface integrals, and here we select the area weighted average and static pressure and press inlet compute. This will give us what the delta pressure is. So 39.22 is the delta pressure because the outlet pressure is going to be 0. So the inlet, compute that gives us the delta pressure 39.22. So now if I go to my Excel sheet, 39.22, and for 0 you can see the delta pressure should be around about 15.9, and if I put 39.22 in there, 39.22, you can see that it's quite far away from the Darcy friction factor because it's calculated 0.0981, where the Darcy friction factor should be around about 0.0398. So the turbulence model and the wall function does have a huge influence on the actual results. So refer that back to this. So again here, what you would need to do is look at the wall function in order to see what kind of difference it does. So just out of curiosity, I'll quickly go back to the viscous model and just say, for example, I put on, you know, I don't know, say enhanced wall treatment, and then initialize this. Initialize, okay. Run calculation. Calculate. Okay, and then if I go to my contours display, you can see that there's a huge difference. Where before it was cooling down a lot more quicker, but now it's not. So, you know, here looking at the delta pressure now, so report surface integrals, compute, you know, it's 22.21, so it's getting a lot more closer. Okay, so the same with the delta pressure. You can also calculate the average nozzle number as well. Now, in order to calculate the average nozzle number, what we need to do is relate it to the reference values. So in here, you need to be able to compute from inlet, okay? And the length is going to be the internal diameter. So the internal diameter here is the kind of height that you need to put in there. Now, when you have a spiral groove, depending on the spiral groove, the height of the spiral groove, this will also change as well because there's more surface area. So at the moment it's 0.02, 20 mil. And then now if I go to area weighted average, click on wall fluxes, and then select the actual surface nozzle number of the wall, press compute, is 41.78. So you can see here the nozzle number is 38 and this is giving me 41.78. So again, the turbulence model and the wall function and the mesh will all have an influence on how accurate the results match with your theoretical value. So rather than going into the simulation all the time to find out what's actually happening, you know, in terms of comparison, what you can do is you can run a parametric function. So what we can do is we can go straight to pressure, go to static pressure, select inlet, and say this as delta pressure. So dP, delta pressure. And then what we can do is select wall fluxes and surface nozzle number, and select the wall and save output parameter as NU, nozzle number. Press OK. But also because we're running different velocities, we need to go into the boundary conditions. And in the boundary conditions, specifically in the wall, in the inlet, we need to go to momentum, and in here we create a new parameter, and we call this one inlet. And we make sure that inlet is selected. Press apply, close. And then what we do is go to the wall, because depending on each inlet there is a different convection. So it's heat transfer convection, so new input parameter, and we type in heat transfer coefficient, HTC. Press OK. Apply, close. Okay, so now we can initialize here. So initialize, OK. And we can go File, Close Fluent. And once we go into our parameter here, you can actually put in your different velocities. So in here we can make that a little bit more smaller, so we can see what we're doing. So we've got 0.2, so 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, and then 0.5. But also at the same time we can put in our convections. So I'm pulling this off from my screen, so I can just copy the heat transfer coefficients. Okay, and then what I can do is I can press update, and it will give me the delta pressure and the nozzle numbers for this turbulence model. So I'll just give it a few seconds. Okay, so as you can see here, all the simulations are done, but as you can see with the results, you know, looking at the nozzle number 38, 45, 52, you know, the nozzle number 41, 48, 55, but then, you know, 79, 85, 78, 72. So, you know, it's in good correlation, but they're, you know, they can be a lot more closer and better, because remember, once you've got this one validated, you then apply the same approach to the spiral groove. Okay, so once this has been done, that's basically the step one for the assignment. So remember, step one here was select a range, which is what you've done. You've then calculated the values, theoretical values. You've generated a 3D numerical model. You then applied, you know, a good mesh, looked at all the boundary conditions in the solver. Then you conducted a turbulence dependency study to ensure the turbulence model is working very well with the wall functions. Then you're going to determine the nozzle number from ANSYS, which is what you've done, and then obviously, you know, you plotted your results. So even though mine has one, you know, you'll have a lot more results on here showing you the different turbulence models, and then you'll select the best one to move forward to the spiral groove. So step two is obviously conduct a parametric study of the groove tube and compare against the smooth tube. So generate 3D numerical model of the groove tube using the geometry provided. Conduct a self-chosen parametric study of the groove tube and compare results with the smooth tube. Okay, so here, looking down here, you've got the smooth tube nozzle number, and you can see here with the spiral groove, it's a much more higher, and then again here the Darcy friction factor showing you a lot more, much better heat transfer taking place compared to the smooth tube. So how do we do this? And here, what parametric studies do you do? So for example, it could be the numerical to investigate the groove design. So you can go from, rather than a simple square, you can change it to maybe a circle, you know, so like a semicircle type of a round smooth tube, rather than a square. You know, you can change this. You can change the height, the width and the height of the groove. You can also look at the pitch of the groove and see what function it is. Now, it's completely up to you what you choose, but remember, whatever you do, you must change one parameter at a time. So the basic analysis of this is the most standard approach is just looking at the pitch. So just by changing the pitch, you can do this whole assignment, you know, for the analysis. So, but again here, depending on the selection of your parameter will determine your title. So if you're doing, you know, the pitch, so it'll be the numerical investigation of spiral groove pitch using ANSYS CFD, or if it's the design, you know, it'll be the groove design, you know. You can also do the tube material, but if you're doing the tube material, you would need to make sure that the heat transfer coefficient uses information from the material properties. So you will need to have different heat transfer coefficients for different materials, because that will make a huge difference. So again, you know, it's up to you what you do there. So let's have a look at the spiral groove. Okay, so we've got a spiral groove which is provided here. It's 200 millimeters, it's got a pitch of 10, and the width and height of the groove is 10 millimeters. Sorry, 4 millimeters, my apologies. So you can see here 4 millimeters and the actual pitch is 10 mil. So let's have a look at our ANSYS. So we can go back to the project. We can duplicate this, you know, it's not a problem. Duplicate it because it'll then take the heat flux and the all the input parameters and output parameters as the same. So what we can do is we just type in groove tube. I'll just change that to capital G. And what we do is we go into the geometry. Okay, so once the geometry is opened up, now what we do is we look at the XY, and we know that in the middle here is going to be the spiral groove. So what I'm going to do is I'm just going to change my view to wireframe because I can basically see what I'm doing here. So in here, what I'm going to do is put in a new sketch. And in that sketch, what I'm going to do is I'm just going to draw a rectangular box. Anyway, doesn't really matter, but over here somewhere. Okay, so like a box like that. Put in a constraint, say that they're equal length. So this is equal to this. This is equal to this. Okay, so that's nice and constrained because I can now give it a dimension. So the dimension I know from here to here is 100. Okay, and I know for a fact that from the middle to here is going to be 10. Ooh, Control Z. Okay, let's delete that one. Delete. Vertical here to here. It's 10 mil, and then general, this one here is 4 mil. Okay, so that's the start of my groove, but then I need to know where it's going to finish. Okay, so what I have to do is I have to go to modeling and then draw in another sketch. It has to be separate because we're going to use a path. So we know it starts from here and it's going to end somewhere here in the horizontal. Okay, so let's give it some dimensions. So we know from here to here is definitely 100. Now remember, this spiral groove is going to go along this path and it needs to end here with this side being here. So what we have to do, we know that this is 4, so this can't be 100 because if it's 100, the spiral groove will be past the 200 mark. So what we want to do is we want to make sure that this ends 4 millimeters less. So here, give it a dimension, Control Z. So what we'll do is give it a horizontal dimension. Okay, so 96. Okay, so 96, that means adding the 4 will make it 100. Okay, so now that we have this, we can now use we can go back to view and make sure we've got shaded exterior. And we can now sweep sketch 1, apply, along the path of sketch 2, apply. We can put in a pitch of 10 millimeters, add it as material, press generate, and then we have our spiral groove. Okay, now as you can see, the spiral groove doesn't really start off nice. So one of your tasks in Design Modeler is to make sure that there's a smooth transition from this surface to the start and end of the spiral groove. Okay, so there's many ways of doing it, but that's one thing that you have to make sure you do. Okay, and you can make the pitch into a parametric function, you know, if you wanted. But again, here, you know, you can change this, do a parameter study, 20, 5, 15, you know, and do a, you know, I wouldn't do 5. That's a bit too crazy. So something like 7, you know, and then that way it'll be good. You can also make the, you know, this into a parametric function if you wanted, you know, or as I even said, the shape. You can even make the shape into a parametric function and do a study that way. So we'll leave it as 4, and we'll do this one as 10. Okay, and here now, obviously, you know, depending on what you've done there, that's absolutely fine. So File, Close Design Modeler. We're then going to go into the mesh, update, and then give it a few seconds for the new model to be imported in. Once it's imported in, the only thing that you have to do here is that in the name selection, you've got the inlet, you've got the outlet, you've got this wall, and then you've got the water zone. Because there's a spiral groove now, there's new surfaces. So what you want to do is you want to go inlet, outlet, right click, hide those faces, go to wall, select the face, click on the screen, press Ctrl A, and then apply. And what it will do is it will select all the faces that are wall. Okay? So generate the mesh, because the mesh is exactly the same. And because you've got the inflation on the wall, the inflation will be on that wall anyway, going all the way through. So you'll be able to see that running along. So if I just show you now quickly, home, section plane, cut that through there, you'll be able to see that the inflation is running all the way through the spiral groove. Okay, so once we got that selection plane, I'll just get that back. As I said, mesh, mesh, update. Give it a few seconds and it's done. File, close design, close meshing. Okay, so now, you know, the setup, you can either click on the setup, but if you have everything, if you've got the best turbulence model, the best wall function, you've got everything set up, you don't really need to go into the setup, because you can just click on the parameter and everything's already there ready for you. So you can just press update all design points. So what I'll do is I'll quickly just pause this video, update the design point, and you'll see the new results that are on here. So I'll just do that now. I forgot to mention one thing. So we have to press stop on here, abort. So because the spiral groove has more, it has a much more surface area, you will actually have to go into the setup because, and this is very important, because in the setup, in the reference value, you have to change the overall diameter now, because the diameter is not 0.2 coming in total, because the spiral groove also adds extra area to it. You have to actually increase the diameter, because it's 4 millimeters going up, 4 millimeters going down. So the overall diameter now in the reference values, maximum height-wise, is going to be 0.028, because it's 0.02 there, 4 plus another 4, so 0.028, initialization, initialize, and then file, close Fluent, and you'll be able to conduct your parametric study. Now, before I do this, there's no point doing the whole parametric study. What I'm going to do is I'm just going to do it for one analysis. I'll just delete that, delete design point, update all design point. Because what I'm going to do is once you've done that, I'm going to just show you how to move on to the FEA part of it as well. So, which is going to be the next thing. So once that's done and I've got a green tick, I can then move on to the next stage. So I'm just going to let this quickly run. Okay, so that's done now. As you can see here, the delta pressure and the nozzle numbers are a lot greater due to the geometry. So what we're going to do now is we're going to move on to the FEA part. Okay, so in order to do the FEA part, we need the final FEA model in order to do this. So what we want to do is we're going to take in a static structural thermal. Okay, so steady state thermal, so not transient, steady state thermal. Put it onto the solution here. Okay, we're going to break the geometry. Okay, because we need to modify this here. And what we'll do is, so let's click on this geometry. Now, we know that the geometry, we don't need the CFD version, we need the actual FEA version, okay? So what we're going to do is we're going to create a primitive cylinder in the YZ plane. We know that it has an overall dimension of, if I have a look, so D0, so D0 is 36. So just 1 second. So just go back to time modeler. Okay. So 18 is going to be the radius. We know it's 400, and it's going to be minus 200. Now we have to add it in as frozen, because if you add it in as material, it will just unite with this one, but we want it to be separate. So we got that there. And then what we're going to do is we're going to subtract, cancel. We're going to go create Boolean, and we're going to subtract target body is our solid, tool body is our tube, apply, generate, and what you'll see is our tube, outer tube, which has a spiral groove inside. And once you've fixed this end, it'll be coming in a lot more smoother. So that's our solid tube that we have. So, and it's a solid there, which is fine. So file, close design modeler. We can then click on the model. And what this will do is this will open up the steady state thermal analysis. And what this does is, because in ANSYS Fluent, we've done the heat transfer coefficient of the water flowing through. And what we want to do is we want to take that kind of surface and apply it to everything that we want on here. So again here, just generate your standard mesh. And you'll see that, you know, is this mesh adequate or not? You know, again, it's nothing to do with the CFD kind of approach. But what we want to do here is we want to make sure that there's enough mesh to make sure that everything's good enough in order to take our results. So give that a few seconds. Let's just mesh in the elements. I had to quickly stop that because it was taking quite a bit of time. I'm just going to put tetrahedron mesh on there. Mesh default, say 2.5, and then just generate mesh. Shouldn't take too long to mesh these. Okay, so we've got something like this, which is absolutely fine. And then here you can see it's got imported loads. So in here, what we want to do is we want to import some loads in. And when we import that load in, it needs to go into the inner surface. So to gain access to the inner surface, we can grab the outer surfaces and then right click and hide those faces, leaving us the inner surface values. Okay, so when we insert the actual temperature load, okay, so in here I can press Control A, it will select those 6 faces, or depending more or less how you do this, and the CFD surface that it wants to bring back from is the wall. Press Enter on the keyboard, okay, and then what we do is we import the load. Okay, so the temperature load has now been imported in onto here. And then what we do is we click on Solution and we look at the thermal error to make sure that there's no error. We look at the temperature. I mean, there's a few others. No, we don't need volume. Delete that one. Okay, so temperature and temperature there. So press Solve. Okay, so now what we can do is we can look at the temperature load going all the way through. Now you can get rid of the mesh on here. I think it was show wireframe, so you can see it like this, a little more better. You can also look at the contour, smooth, or you can change it to ISO lines, you know, smooth. You can show it with, yeah, a bit more nicer that way. And you know, you can create a mid-cut plane going through here as well to show what's actually happening inside. So again, section plane, you know, creating a mid-cut plane for the middle to show what's happening to the temperature inside here. Now, thermal error, you can see that it's saying actually, you know, because the mesh isn't as good enough inside here, you got a few issues. So again, you know, improve that mesh inside. You know, it would definitely give you a good, much better understanding of what's actually happening in here as well. Now, you can also, in the geometry model, insert a construction line. Okay, so you can create a path, and we know that the outer thickness, you know, you can create it on the surface, you can create it in the middle. So we know that this is 4 millimeters, this is 20, this is 24, and then the outer surface is 40. You know, on the actual thing. So what you can do is you can create a path line to get some more measurements from here. So we know it's minus 200. We know it's plus 200. And we know if I said 20 mil, it comes to the top surface, 20 mil, top surface. So you can see that that will actually take measurements from the top of, oh, it's gone a bit more, not the top surface, 18, sorry. 18. And that's the actual, at the top surface. So if I went a couple of millimeters below, so say 15, you know, that's a couple of millimeters above, so say 16. You want to go halfway between the top surface and your spiral groove. So what that does now is I can go to my solution, I can actually put in a thermal temperature, and rather than doing that, I can click on path and click on path body. Okay, and then press solve. Okay, so that's how there's the temperature load, you know, of what's happening. But fundamentally what's happening here is we've got that taking place, but we also need to look at the assignment, because the assignment says once we generate the 3D model, make sure the boundary, conduct F-side modeling using temperature distribution from the CFD, which is what we've done, as the internal boundary condition for steady-state thermal analysis. So the temperature distribution of the tube, The outside of the tube is subject to convection with a heat wave of 5 watts per meter squared Kelvin. So first of all, we need to know this is structural steel, which is very good. And what we want to do now here is we want to put convection on. So we want to see all of our show hidden faces. Okay, so we want to put convection on this surface, apply. Now what we want to do is go to units, metric. So here will be 5 watts per meter K. Solve that again. Okay, so now you can see the thermal error still there, but you can see the temperature is a bit more different now, and you can see the temperature load is a little bit more different now as well, because there's convection taking place on the upper body surface of it. So we have everything ready here. The only thing that needs to be improved is the mesh, but here you can take these results and put them into, you know, your answers for. And again, I wouldn't do it for every single velocity. Maybe take a maximum of 4 different or 3 different velocities, minimum 1, but you know, you want to show your capabilities here. So file, close mechanical. We then come here, take a static structural, and we put it onto the solution and engineering data here. Okay, so it uses the same model, and what we do is we click up on the setup, give it a few minutes. Okay, so that's opened up now. It's obviously copied in the actual section plane as well. Okay, so you can see that it's imported the loads here. Okay, the temperature loads, thermal errors, temperatures and everything that's come through. Okay, so what we want to do now is we want to run the static structural analysis. So the imported loads is imported in the body temperature. Okay, but also at the same time, what we want to do is we want to bring in the actual fluent pressure forces as well. So the solution of this one needs to also come into this setup here as well. So when we double click on this one again, it will update. And rather than just bringing in the temperature, it will also bring in the pressure forces, the delta pressures, into the actual simulation. So you can see here B5 is also opened up now again. So here we insert pressure. Now the pressure is going to go into the internal thing. So again, very similar. What we want to do is we want to just turn these off, so, or hide them, hide faces. We want to click on this one, detail view, Control A, apply, and then here we select the wall, enter, and we import our load. And what it will do is it will bring in the pressure forces, as you can see here. Okay, and we've got our body temperature, we've got our pressure forces, all right. But at the same time now, what we're going to do is we're going to show all the hidden faces. We're going to put some constraints in. So in the static structural environment, we want to put some fixed supports. So this one and this one is going to be fixed support. Okay, so that's fixed. And now what we can do is we can do our analysis, so total deformation, and again here, error, for structural error, we could look at the equivalent stress, and if you wanted to vomit a strain as well, so just press solve. So again here, what you might see is it looks something very similar like this, but don't worry, this is just basically auto-scaled. We want to go to true scale, and as you can see here, the actual, should we say, let's have a look at deformation here. It's very, 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 very minimal, you know. But you can, again here, you know, talk about your structural error. So the mesh needs to be improved. The mesh is not good enough. The mesh needs to be improved a little bit more for structural error. And then again here, the equivalent strain stresses, you can see where the actual stresses are taking place. So obviously on the edges and then around the spiral groove as well. So very similar like the other process, you can actually create some construction geometry. So hopefully, fingers crossed, if you've created the structural geometry in the first section, you might be able to see in this one as well. So path, so the same path exists on both ones. So we'll press solve on here. You can see the deformation taking place on there. So again, here, that's something that you would do. So I'm not looking for FEA analysis for every single spiral groove parametric study, but it would be nice to show one or two, maybe some of your best designs. There's no need to do one on the smooth tube, but it would be nice to see it on the spiral groove to show that you can do the FSI. So hopefully, fingers crossed, that's everything that's needed. So let's just refresh. So we've done the thermal analysis, we've done the static structural, and to evaluate the material deformation and stress, and present your results. So again, here, presenting these results is completely up to you how you do it. You can use CFD post. Do not use screen grabs. You can actually just, image to clipboard and then just paste it into any Word document, and it'll be a much better kind of high-res images. Now remember, you'll be presenting this as a paper, conference paper, so we're not looking for a huge number of images. Think about what best images to put in, what will really complement your discussion and the way you describe your results. Okay. All right, thank you very much.